Okay, it is now 10 o'clock, so I'm going to go ahead and start here. If you notice, there is a poll that should be up just to get some demographic information for the university and for us to better understand our audience so we can serve you better with our programming. So go ahead and fill that out while I introduce today's topic. So welcome. This is the first webinar in the 2022 Water Quality Wednesday Winter Programming Series. We're so excited to present the first topic today, which is how can we manage phosphorus to protect our water? So here in Northwest Ohio, where myself and our 4 other water quality associates are stationed, phosphorus is a hot topic because of its potential effects on water quality. Now, although we recognize not all of our viewers may be from Northwest Ohio, phosphorus is still an important topic when it comes to water quality across the state and even the nation. So with that, let's get started. As I mentioned, this is only the first webinar in our Winter Water Quality Wednesday series, and listed here are the 4 upcoming webinars we have planned for 2022. They're all from 10 to 11:30 a.m. and you can register for any and all of the sessions at the link at the bottom of the screen, which is go.osu.edu/WQW, or you can scan the QR code shown below. And we'd love to have you join us for the rest of our sessions, but if you can't, they will be recorded for later viewing and posted on our YouTube channel, and I will put that link in the chat. If you register for a session and you can't make it, a link to the recording will be emailed to you when it becomes available. So good morning, everyone. I'm Rachel Cochran, your host for this morning. I am the Water Quality Extension Associate covering Paulding, Defiance, and Van Wert counties. Below me on the screen, you will see Paige Peterson, who could not be here today, but she put in a lot of work behind the scenes helping to plan this webinar. She is the Water Quality Associate for Henry, Wood, and Ottawa counties. And last but not least, we have Jordan Beck serving as moderator for today's webinar, and he's the Water Quality Associate for Fulton, Williams, and Lucas counties. If you'd like to contact any of us, our information is listed here on this slide, or you can find that information for us and the other associates at waterqualityextension.osu.edu. Now I'll turn it over to Jordan to introduce today's speakers.
Good morning, everyone, and thanks for attending the webinar today. We'll go ahead and get started. Dr. Chris Winslow will be our first speaker. Chris coordinates Ohio Sea Grant's Great Lakes research with agencies and universities, as well as assists in research, curriculum development, and student recruitment at the Ohio State University's Stone Laboratory. Chris earned his doctorate degree at Bowling Green State University, with research focusing on interaction between the native smallmouth bass and invasive round goby. So with that, I'll allow Chris to share his screen and he can get started.
Thank you, Jordan. Thank you, Rachel. Let me see if this works. Can you hear me first?
Yes, we can.
Great. All right. And let me know when you can see my PowerPoint. And I'm going to turn it to slide view and see if that works. How's that look?
Very good. You're all set.
Okay, great. Well, thank you again for the introduction. Thanks for the opportunity. I look forward to hearing from Libby Dayton later in the presentation today. So that's always great. And look forward to some Q&A. So basically what I'm going to walk you through is just kind of level set everybody on nutrients. As Rachel referred to, maybe not everybody on the call is from the Northwest Ohio and deals with the harmful algal bloom in Lake Erie. So I'm going to spend some time kind of getting everybody on the same page. So I'll talk about the source of nutrients today, the research that's ongoing and being done and that has been done related to this nutrient issue and harmful algal blooms. And then also I'm going to spend some time talking about some gaps that we need to be continuing to address. Just want to mention the logos at the bottom. First to the left, NOAA. When you mention a Sea Grant program, that is a NOAA funded program. So Ohio Sea Grant is one of 34 programs across the country. So any state that bumps into an Atlantic, a Pacific, the Gulf, or Great Lakes has a Sea Grant program. So that's why the logo is on the right. That's what we are. Sea Grant programs based out of NOAA. In the middle is the Ohio State logo. I need to update that one because actually now we're not just at Ohio State University, but I have the pleasure of reporting up through the College of Food, Ag, and Environmental Sciences. more specifically tied into the School of Environment and Natural Resources. So it's great to be within Dean Kress's shop and to work with the phenomenal researchers and education outreach folks within that college. So here's what we've got, folks. This is the history of blooms in Lake Erie. Granted, this slide only goes to 2019 for us, but basically what you're looking at is the western and part of the central basin of Lake Erie. That's the polygon you're seeing. Each year is what we call a heat map. And so the warmer the colors means more severe bloom, and the cooler the colors mean a reduced bloom, and then black is non-detect. So we have clearly had this issue since the early 2000s, starting in the top left-hand corner here. But we can also show that since 2002, we've ebbed and flowed. So some years like 05 here and 2012 were fairly light years, but then things like 15 and 11 were large blooms. And so we're working on why that variability exists and how can we address issues within this variability. Why is Lake Erie always on the radar when we talk about HABs as far as the Great Lakes? This image is trying to show you that. So this is the depth profile of the 5 lakes. So again, Superior here to the left, Huron and Michigan overlaid on top of each other, Erie and Ontario. And what this figure should show for you is how basically shallow Lake Erie is. And so what we always say, it was the environmental theme of the late 60s, early 70s, that the solution to pollution is dilution. You don't have a dilution factor in the Great Lakes when it comes to some of this nutrient runoff. It's such a shallow system with a lot of light penetration, especially on the western basin side, that we're going to have to contend with anything that enters this water body. But to put this figure into better perspective, this is land use in the watersheds. So what you're seeing here, each bar represents all 5 of the Great Lakes. So Erie on the far left, all the way to Superior. And what we're going to do is concentrate on the Lake Erie watershed. So I'm going to walk you from the bottom of this bar graph all the way to the top and talk about what is the land in the Lake Erie watershed that ultimately runs off and feeds into Lake Erie and the Great Lakes. So at the bottom, light blue is urban. So of all the 5 Great Lakes, we have the most. So we're in first place with the most amount of people living in this watershed. So as we address nutrients, we have to make sure that we're not just talking about things like ag, although it's a contributor of these nutrients. We have to talk about how we humans on the landscape contribute to this nutrients, whether it's our fertilizer application in our suburban and urban places, our golf courses, our wastewater treatment plants. So we, as people living in the watershed, are not removed from this. The orange represents ag, and again, we're first. Ontario's watershed has an abundant amount of ag also, but when we address this issue, ag needs to be at the table. I'm talking about how they can change some of the practices on the land to help reduce the nutrient loss from that system. The gray is grassland. It's pretty negligible across all the Great Lakes, so I'll skip that. But for forests, typically we view these as non-excess contributors of phosphorus. There will be some runoff of phosphorus and nitrogen from these forest systems, but for the most part, they're non-contributors. But you will see that we have the least amount of forest in the watershed relative to the other 4 Great Lakes. And then the last bar that you're seeing here is wetlands. And the reason why I bring this up, and I could put the word least here again, we have the smallest blue bar relative to the other 5 Great Lakes, but I always put the number 10%. It reminds me to tell any audience I have the pleasure of speaking with that we only have about 10% of historic Lake Erie wetlands remaining. Many of those have been drained for ag or drained for growth of communities, either urban centers or suburban outlying areas. So are we going to get those 90% of wetlands back? Probably not. But towards the end of the talk, I will revisit what is going on more specifically within the Ohio Department of Natural Resources to address this wetland loss and introduce this as a tool for nutrient reductions. Just some pictures. I like to throw in pictures every time I throw out a graph just to get people back. This just shows you some of the blooms in Lake Erie. This is 2011 up by the Lake Erie Islands. This picture is also in that same year. This is out by Marblehead, which is over by Put-in Bay, Port Clinton, in that area. And this is a colleague of mine, Dr. Richard Krause, who works for the USGS with his family out on a pleasure cruise. So nutrient sources today. In this western basin, the Maumee and Sandusky rivers are the largest phosphorus loaders. So most of the phosphorus is coming out of those systems. When you look at that phosphorus, most of it is coming from what we call non-point. Okay, so 87 to 93% of this phosphorus is coming from non-point. What that means is it's not coming from a pipe. Okay, it's diffuse runoff from the landscape. We know where the pipes are. EPA tracks these because of permits that are given to those discharges. But most of the phosphorus, if you remove what we know of coming from point sources, is coming from non-point. This slide reminds me with this parenthetical comment is this is also where most of the nitrogen is coming from. When we hear about harmful algal blooms and this growth, we always hear phosphorus mentioned in the news and the media, but we also know that nitrogen helps increase the size of these blooms. But perhaps more importantly is nitrogen is tied to toxicity. And so the more nitrogen you have, the higher probability that those blooms will go from non-toxic, just green, annoying blooms to something that produces toxins. Within these two rivers, we now know 87 to 93% comes from non-point. Well, if you look at the land use, like the figure showed you before, ag is the dominant land use in both of these rivers. Greater than 70% of the landscape is covered by ag practices. This is not me saying ag is the problem and only the problem, but it is saying if we're going to do a heavy lift to remove our nutrients, we got to target a lot of our efforts and assistance and incentives and things like that to the ag community. I also want to mention, this slide helps me with this, is that we've seen from data that 70 to 90% of the phosphorus, the loading, the amount of phosphorus that makes it into those rivers is occurring during 20% of the flow events. And so basically what this tells us is that usually about 10 storms, depending on the year, drive most of those nutrients into the system. So this tells me not to just tell you that this is a nutrient management concern or nutrient management effort, but it's also a stormwater climate change effort. This has a lot to do with water management. So that's high level. We know a lot is coming from ag, again, not through malicious intent, but just because of land use and the nature of that business. But I want to put some other numbers up here to kind of frame that. So since the mid 1970s, we've seen a drop in the amount of phosphorus coming from wastewater treatment plants, or WWTPs. So back in the 70s, when the lake was considered dead, back during that industrial revolution, a lot of phosphorus was coming from wastewater treatment plants. But since then, we are now, if you add up all the pipes that discharge wastewater treatment effluent, so those point sources, it only adds up to about 9% of the phosphorus at the edge of the Maumee River when it meets the lake, when it meets Lake Erie. So 9%, if we got to address the situation, we got to at least cut that, close to half. So wastewater treatment plants aren't removed from this issue and need to play a role. We people living in the watershed need to play a role. CSOs are another one that gets some attention. A CSO, if you're not familiar, is a combined sewer overflow. These existing communities are typically older. And what happens is that all the water leaving our homes, or our wastewater, joins with water coming off of streets and parking lots into a combined sewer overflow. And this is fine. Mostly our wastewater treatment plants can treat the phosphorus or remove some of these nutrients from these discharges. The problem is when heavy rain events come, the water coming from river or from parking lots and streets overwhelms these systems. And so a CSO discharge basically means there are periods during the year where that water is not treated and the phosphorus is not reduced and it's discharged directly into our water bodies. Thankfully, 40 of the 62 communities that have these CSOs have control plans in place. So they're marching to remove these combined sewer systems. In 2013, just to give you an idea though, even if you added up all of those discharges during those crazy storm events and added up the phosphorus typically associated with a CSO discharge, it's only about 1% of the phosphorus. I'm not saying we shouldn't address these. It's pretty disgusting that we're releasing raw sewage and the pathogens and viruses associated with that into our receiving water bodies, but it's not driving the bloom. I do bring up this last bullet because the news fairly recently, maybe 4 months ago, found out the city of Maumee was violating its discharge. So they were permitted on a year to discharge 25 million gallons of untreated sewage because of these CSO events. It was determined that over about a 20-year period that they were violating that level. And in some years, up to 120 million gallons of CSO discharge. But even if you add up those extreme events that Maumee is tied to, that would still only be about a 1% of phosphorus. So it's not good that Maumee violated that permit. It's not good, again, that we're releasing the CSO water. But those events, general CSOs and the air on Maumee are not driving these blooms. We do know that septic systems in some communities are not up to par, and they are releasing excess nutrients, some of them through direct discharge. But even if we go out through EPA and the Department of Health and estimate these discharges, it only adds up to about 4% at the mouth of the Maumee, again, where the Maumee enters Lake Erie. Only about 4% of the phosphorus can be tied back to septic. Gratefully, in the state of Ohio, our legislature and our governor are providing low interest and no interest loans to help people fix these CSOs. I want to talk about Scott's Miracle-Gro. So basically, this is a fertilizer company for suburban, in this case, for suburban application. Since 2013, Scotts has removed phosphorus from its maintenance fertilizers. They recognize that most of the soils in the Great Lakes region, more specifically in Ohio, don't need phosphorus to have a green grass. And thankfully, Scotts in this part of the country leads 95% of the market share. And so we can confidently say that when we do add fertilizer in our suburban and urban, even some of our rural landscapes, it does not contribute to excess phosphorus. And the last one I want to mention before I get into a further discussion about legacy phosphorus, I want to talk about internal loading. And that's a fancy science term for basically what is the contribution of phosphorus already in the lake. So during storm events, the phosphorus at the bottom of the lake making it back to the surface and driving blooms. We've done some research on this. We did some heavy experiments in 2014. And 2014 showed that it's only about 3 to 7% of the phosphorus that is being used by those organisms in the lake that comes from the lake itself. So again, if you add up all of these things, all contributing, all need to be addressed as we move forward towards solutions, it leaves that about, depending on the year, 65 to 85% of the phosphorus coming from ag-related practices. So here's where we're at, folks. What you're looking here, this is particulate phosphorus. So if you were to take a water sample and run it through a filter, it's this brown or green gunk left on the screen. And what you can see, I'll orient you, this is basically the concentration of this particulate phosphorus through time. So every dot on here represents a data point from basically 1978, I think is where it starts, or something in that area, or 72, all the way to roughly present day. And what you can see is that we did have an issue early on in the Great Lakes when they were considered dead, but reductions in the wastewater treatment plant contributions and other things had dropped that pretty well. The black line represents the 5-year running average. So taking the 5 closest data points to this point in time. And then the gray line represents where we need to get as a target. It's basically a 40% reduction is what the lake is asking for. So that's total particulate phosphorus. In 2020, it was at 0.47 milligrams per liter here, and our target is 0.23. Let's turn this around and not talk about particulate phosphorus, but let's talk about dissolved phosphorus. This is the phosphorus that when you run the water through a filter comes out clear at the bottom, but there is dissolved phosphorus in there, just like you would dissolve sugar in your coffee. Same thing, each dot represents a specific year. The black line is the running average and the gray is the target. Again, high in the late 60s, early 70s, dropped below our target in the mid 90s, but has been creeping back up and has stayed up for the last, you could argue, 2 decades, so since the early 2000s. In 2020, this data that I have here, we were at 0.075 milligrams per liter, and we need to be at 0.05. So still well above where we want to be going. So what I always tell people when I have the opportunity to speak to audiences is that to get to the solution, which is a 40% reduction in phosphorus into Lake Erie, my opinion is that we attack it through 3 buckets. The first bucket is the 4R nutrient certification or stewardship program. Basically, what we're doing is working with the ag community to talk about right rate, right time, right application, and right source of these nutrients. And there's been great training programs run through OSU's extension program. I think Libby will talk a little bit about the application and tillage in her talk, but we need to think about how we engage with phosphorus in a given planting year, the fall before the season or the spring before the season, and what we can do, best practices on the landscape to reduce those nutrients. Bucket 2 is legacy, and that's what I'm going to spend a lot of the rest of the talk on, is legacy phosphorus and how we deal with this nutrients that's already in the system from 40 years ago, and how our relationship with phosphorus 40 years ago, and how that is still leaking into the system now. And the last one I don't want to ever lose track of. Yes, this is a phosphorus nitrogen nutrient management issue, but it's also a water management issue. And so we've got to think about how we continue to grow crops and feed the mouths of our country and other countries in a climate change scenario. I'm going to skip over that one. So let's talk about this legacy. This is a lesson we learned in 2019. And if you don't remember back to 2019, the fall of 18 was very, very wet, and the spring of 19 was very, very wet. And so we learned some things from that. It was abnormally wet. So let me orient you to this figure, and then we'll talk about what's going on here. This is the bioavailable phosphorus that enters the lake from the Maumee River. Okay, and this is discharge from that river. And what this is cool is this is what's called a correlation. So we know that if you look at each one of these years, so that's a data point from 2000 to 2018, they all fall so nicely on this line. Okay, so if you were to ask somebody, if you didn't see this line here and say, hey, can you draw a single line that represents all of these data points? That's what it would look like. That's a correlation. So what it's saying is that if we know how much water is coming down the river, we just slide up to that line and come to the left, and it'll tell you with a fairly good accuracy how much phosphorus is probably in that water. Okay, if you slid the line up here, right, and slide over, it would tell you this is the scenario. And so this line basically gives us some prediction capabilities. So if we tried to map 2019, which is I'm going to put up here in a yellow dot, we would have expected it to be somewhere on this line or very, very close, like a lot of these dots. This is where we would have expected it because we knew that a lot of water, I told you it rained a lot in 18 and early 19. This is where the water was. We measured this. So you would have assumed the phosphorus should have been just below 600 metric tons. It actually sat here. Why? Why with this great prediction since 2002 to 2018 were most of these lines on this or dots on this line, but in this year they weren't. So let's talk about that. Why were the loads 24% lower than expected based on flow or discharge right here? Okay, so let's look. In 2019, 41% of land was unplanted. That's what this normalized difference vegetation index is showing you, the NDVI. So in 2019, if you look, the ground was brown in the spring, so May, got a little bit greener. Oh, I'm sorry, this is 2018. So in a quote unquote normal year, brown in the spring when the crops aren't growing yet, gets greener and greener and darker green through time. In 2019, because we went tons of land unplanted, it stayed brown longer and never got as green as we would have expected. Additionally, only 46% of typical commercial fertilizer applications were sold. Okay, so when we went out, typically when producers go out, they would buy fertilizers and apply it to the land in 18 and 19 because they couldn't get out in their fields because of rainfall. 46% of commercial fertilizers were purchased. We also estimate that about 15% of typical manure application was out there. So not the amount we normally put out, but only 15% of manure was applied. And so what this tells me and what I want to convey to you is that in 2019, we did the 4R steward certification in spades. We did so well not to put any fertilizer down in a given year. Okay. And so that's why you are seeing this trend. This yellow dot went from expected to actual because we cut our fertilizer application following that one bucket, the 4R stewardship program. But why, if we address the 4R stewardship program, did it not go from here, where we would have expected, all the way down to the target or below? And the argument is water management and that other third bucket of legacy. So let's talk about legacy. So why legacy sources matter? The first thing is that phosphorus transport in Lake Erie is a combination of both legacy and contemporary P losses. So contemporary meaning current application. So we know that when you get a rain event, nutrients leave the fields or leave the landscape and then go to the river. Some of that is newly applied nutrients from the fall or spring of that year, and some of it's old applications that are still in the soil. The problem with legacy is it can also serve as a chronic source for decades. If you get a rain event, not all that old phosphorus runs off. It hangs out, and it hangs out for quite a while in some cases. And so what it says is that as we address the 4R stewardship, we've got old sources that are going to run off for decades. Also, what I'm worried about is we're doing so much on our lands right now through Governor's H2 Ohio initiative and through farmers just really being engaged and stepping up. Unfortunately, this legacy contribution, this old application, 40 years ago application, can mask all the great things we're doing right now. It can mask some of these present day conservation efforts. And so the last thing I'll leave you with on this is basically to effectively manage phosphorus, we need to think about where that primary source is. So what a farmer does on their field may all need to be just current best management practices because they don't have legacy. So right rate, right time, right source, right placement. But in some fields, doing that may not matter because their largest loss is old legacy phosphorus. And so in that case, you got to think more about buffer strips or phosphorus retention basins or wetland placement. So the strategies we deploy are going to vary depending on whether your source is legacy, contemporary, or a combination of both. So I want to shift a little bit to what we're doing on the research side of things. And I don't want to dip too much into Dr. Dayton's talk, so I'm going to move through some of this a little quickly. But I want to talk about the HABs, or Harmful Algal Bloom Research Initiative. So in 2015, when we had the Toledo water crisis, the state of Ohio really stepped up. Basically, the Ohio Department of Higher Education mobilized $2 million a year starting in 2015 to fund academic institutions to conduct research to inform management decisions. So basically, Ohio Sea Grant, in partnership with the University of Toledo, every year we sit down with our state agency folks and say, what questions, research, academic questions you need answered relative to nutrients or HABs that will better help your state agency manage this issue, this nutrient issue and this harmful algal issue. So I'm going to categorize them in four categories. The reason is because to date it's been about $10 million have been spent in about 80 projects. And we do not have time to run through 80 projects. But under HAB Research Initiative, or we call it HAB-RE, we've provided solutions to help basically treat safe drinking water. We don't want another Toledo crisis, so we need the research to show us how do we, in our water treatment facilities, remove those toxins if present. We need to know about human health. We got to figure out when you do get exposed through drinking water, hopefully not the case, but through recreation and other routes, what is the ultimate impact to you from a human health perspective? The next one is how these blooms behave. Why are they showing up when they show up? Why do they disappear when they disappear? Why do they produce toxins sometimes of the year and not during other parts of the year? Are these blooms always at the surface where we're exposed to them? Or are they at the bottom of the lake where the water intakes are? And so we needed to know more about the bloom behavior itself. And the last one is nutrient runoff. And we're spending a lot of time and a lot of financial support to address how do we slow nutrient runoff, whether contemporary application or legacy. So these are the priorities that are coming out of the agencies. I'm going to go through these again really quickly, but feel free to reach out to Rachel. She has this PowerPoint, or Jordan, and they can provide it to you. Or I can give you my email address and we can walk through all of them. But the DNR is doing a lot in identifying, constructing, and managing wetlands. They want to know what role wetlands, new ones created on the landscape, about 100 are slated to be built or are already built to basically replace those ones that we lost historically. Ag has given us so many priorities. It's been great to work with the Department of Ag. They want to look at manure management and manure application practices. So how do we better store our manure and how do we better apply it when we're going to move it to our fields? They want to know about subsurface placement. So this is the banding or injecting of nutrients under the soil rather than setting them on the top. Again, if you get erosion, runoff from the surface, if those nutrients are on the top and not banded or injected, they're more likely to run off. So they want to know if a farmer's going to do this, they better know what it's going to cost them. So what is the benefit relative to the cost of this practice? We need to figure out water management. So how can ag better adapt to these multiple 3 and 4 and sometimes 6-inch rain events? Drainage, retention, and detention. So if we're going to hold that water back on our fields, how do we do it? How do we do it so that we don't impact productivity of our fields, but also we don't want to hold it back such that it actually becomes more concentrated with phosphorus or nutrients? And they want to know why farmer participation is where it's at. We have a lot of amazing farmers stepping up to be part of the solution and investing in their land and getting money from the governor and the state agencies to help them. But there are some that are somewhat hesitant or reluctant, and we're trying to figure out why, what's the barrier to them engaging more aggressively than they are right now. The Lake Erie Commission, it's one of our agencies in Ohio too. They want to look at the effectiveness of the governor's H2 Ohio program that's in place. So again, this is money invested by the governor to help out these agencies, EPA, DNR, health. And then we have a domestic action plan. So it's a plan on how we think we're going to get from where we are to where we need to be in the phosphorus space. They want to study pilot watersheds. So can we compare 2 watersheds, do a lot of best practices in one and leave the other one fairly untouched and see how quickly we can get to that 40% reduction. And then they want to address always this cost benefit analysis of the 10 approaches that the EPA, that the H2 Ohio program through ag is saying we should be doing to slow contemporary losses. And then as usual, the EPA and health, really they're concerned about source water protection. How do we protect drinking water and human health? So these are these top 10 practices. So under the governor's H2 Ohio, this is specific for the Department of Ag. They're getting funds somewhere in the $60 to $7 million to basically assist farmers in deploying these top 10 practices. Now I should correct top 10, that's why it's parenthetically. Right now, we're only funding the first 7 practices. So soil testing, variable rate technology, subsurface nutrient application, manure incorporation, conservation crop rotation, cover crop usage, and drainage water management. Not a lot of going into 2-stage ditches right now or edge of field buffers for ag. And this last one, number 10, wetlands, really falls to the Department of Natural Resources. So I'm really curious about drainage water control structure and how it impacts soil health. We're not doing practice 8 and 9, as I just mentioned, and then number 10 is being done by the DNR. So really they're looking at these wetlands as ways to filter that water to remove not only nitrogen and phosphorus, which is the primary goal, but what other things are they removing from that runoff water? I think this is the last slide I had, but basically what this talks about is this legacy again. And I want to bring this up at the end of the talk because legacy is an issue for the reasons I mentioned earlier. It's a chronic source through time. It masks the great things we're doing on the landscape right now. And it influences what management practices you would deploy. So soil test phosphorus can decrease if we stop applying to these legacy fields. So if we say, all right, we've already got too much phosphorus out here from historic applications, let's stop applying. But what we've seen in a couple stories, and this comes out of Fulford and Coleman, is that this will take time. So we need to talk about a lag effect. If we're going to say we're going to see a solution in Lake Erie overnight, we need to know that some of these sources of nutrients are going to take a while to resolve. And I want to know how just farmers increasing soil health through things like cover crops and not tilling, but banding and injecting will play a role in how quickly we can draw down this lag. But let me walk you through it. This is a field. It's not named, no specific information here, but a field in Clark County, Wayne County, and Wood County. And what you're seeing is the dotted line represent the soil test, or I'm sorry, the vertical axis represents soil test P, and the two dotted lines here are the sufficient concentration ranges. So when we recommend to farmers, Steve Coleman helped with this, the tri-state fertilizer recommendation, we're telling farmers they need to be between these two dotted lines to basically ensure they're going to get maximum yield. So the red line basically says if we stopped applying to these fields, how quickly does it go from where it was, which was in the band of where you want to be, to outside that band. And so for Clark County, if you stop applying fertilizer on one of these legacy fields, after 4 years, that phosphorus that was old or in there for a while needs to be replenished. In Wayne County, not the case. You've got almost 8 years here before you even leave that range. So that loss of this legacy phosphorus from this field is very slow. And in Wood County, it's odd because it stabilizes, then you get a drop, and then it comes up, and then it drops. And so knowing why this is the case, why in some years did that soil test P come down or stay stable, and what happened when it didn't. Now, one time, the blue triangle means applying at removal rates. Okay, so basically saying, I'm going to put down there what I think my corn or my wheat or my soybeans is going to draw. And what you can see, and even in these scenarios, applying at one time in some fields, it means you maintain where you were before. Here's where I started in 06, and here's where I am in 2013. In other scenarios, it's a slow decrease. So one time of the recommended rate is still a slow loss, but it is very slow. And then at 2 times fertilizer rate, you can see what happens is that, again, you can increase the soil. There's tremendous variability. And so the take-home message I'd really like you to see here is that if we don't apply to these fields, losing that legacy is going to take a while. And also, not only take a while, it varies by field and by county. So with that, I'd be happy to take questions, but I think from instructions, I'm going to stop sharing and pass it over to Libby Dayton. So if you have any questions, I think Jordan will facilitate that dialogue at the end of the talk. So I will wait by for questions at the end.
Yeah, thank you, Chris, for your presentation. It was very informative. Glad to see the background on what's happening in Lake Erie. And yes, we will take questions at the end. I forgot to mention it before, but feel free to put those in the Q&A box anytime during the presentations. Looks like Libby's got her screen up, so I'll go ahead and introduce Dr. Libby Dayton. She is a soil scientist in the School of Environment and Natural Resources at The Ohio State University. Libby received a Bachelor of Science in Environmental Science from the University of Massachusetts at Amherst, and she got her master's and PhD in soil science from Oklahoma State University. As part of the Soil and Environmental Chemistry Research Group at Ohio State, Libby is working to give farmers the tools they need to make management decisions that will assist them in reducing their contribution to a major water quality issue. With that, I'll turn it over to you, Libby, and we look forward to your presentation.
Oh, am I muted? Is that on now?
You're good now. Yep, we can hear
Sorry.
you, and we can see your
Thank you.
slides.
Okay, so I took some notes of what Chris was talking about. I think a lot of our stuff meshes together really well. I hope what I'm going to show goes a little bit farther, a little bit more specific about what's going on. So let's see. So the data that I'm going to be showing today comes out of the On-Field Ohio project, which, you know, many people may be familiar with, maybe not. But it was our work to revise the Ohio Phosphorus Risk Index using field scale, edge of field, runoff water monitoring data. My slides aren't advancing.
So Libby, for me, sometimes if you go in the bottom left-hand corner, they'll show you little forward and backward arrows. So maybe you can use it from the screen rather than your keyboard. There you go, right next to the pen.
Yeah, I see it. It's just, okay.
That one should do it.
Okay, there. Okay, well. So the question we were asked to talk about today is how can we manage phosphorus to protect our waters? So I apologize in advance. I brought a lot of data. So today I want to show the raw runoff data summaries of what we actually see coming off the actual fields that we were collecting data from. Then we'll talk just a little bit about how that data was used actually to develop the On-Field Ohio tool. Then we can broaden our scope and look across Ohio, because we were asked to not only focus on the Western Lake Erie Basin, but talk about all of Ohio. And then I always like to finish on a hopeful theme. So is there any hope of us, of farmers, of Ohio agriculture meeting the water quality targets? So let's start right in with the raw runoff water data. So a little bit about how we collected the data. We were collecting tile runoff and surface runoff from 29 fields across Ohio. We looked at more than 2,000 runoff events. We collected more than 14,000 runoff samples. And every year we collect very detailed crop management information from our participating farmers. And I'm very grateful for their participation. So the samples come into these muddy bottles, and the bottles come back to the lab. And what did we measure? So again, we measured in each of the samples the runoff concentration for both surface and tile. And I think Chris did a good job of making this distinction. You know, the runoff total P is all the mud, every single thing that came out in that muddy bottle. But then we can filter a fraction. So we just see how much phosphorus is dissolved in that sample. So we have the dissolved reactive P, and then in the unfiltered, and we digest the heck out of it with really strong acids, we get the runoff total P. So runoff total P minus the dissolved P is the runoff particulate bound P. Then the samplers also gave us flow volume, how much water came off the field during a runoff event. So concentration of what's in the water times how much water tells us the load, or the pound per acre of phosphorus coming off in that runoff event. So again, for every runoff event, for both surface and tile, we're measuring dissolved P, particulate P, total P. We measured runoff suspended sediment, which is just how much mud was in that bottle. The runoff flow volume. Every year we look at the erosion potential using the Russell II program. And we did it for each crop year and averaged across the rotation. Every year we went out, we did soil testing. And as I say, we collected very detailed farmer management information. So these are the soil test levels for our fields, and I probably need to adjust these based on Steve Coleman's new levels, but also this was also including wheat in the rotation, if wheat was in the rotation. And these also are malics, and the graph that Chris just showed you was in Bray. But anyway, just in general, our fields were mostly within the agronomic range, but we did have a few that might be considered slightly deficient, and then we had a couple that were really crazy high. So we had a nice range, which is what we like to see when we're doing research. So I'm not going to belabor this a lot, but this I wanted to show you because we're talking about, if we're talking about the background, everyday baseline runoff dissolved P, that's these black dots. The red dots are fertilizer and manure application spike events. So there's actually thousands of dots on this graph, but what we see, and this is soil test P, so what we see is as the soil test P goes up, your background baseline runoff dissolved phosphorus, this is in concentration, goes up, which I think we all know that. But I thought this was interesting to overlay the spike events on top of it. So there aren't, I mean, considering there's thousands of data points here, there's not a huge number of spike events, but you can see they can be very dramatic. These really high ones actually were all MAP applications. And this was MAP applied in the winter. It was possibly frozen ground. Then there was it was surface applied, and then there was big rainstorms. And so briefly, we had these huge concentration spikes. But the other thing to notice about these is each one is a separate sampler, a single sampler on a single field. And you notice that the concentration of dissolved reactive P in the absence of a fertilizer problem stays pretty steady eddy, year in, year out, winter, summer, it doesn't care, because it's all related to what is your soil test level. So now this one, I'm going to belabor a little bit, go a little slower here, because these are summaries across our samplers, across years, of the range of what we were seeing. So for each of these, this is a single sampler. This is field 23, sampler 3, field 23, sampler 3. But this is the dissolved P with the little green dots. And this is the runoff particulate bound P. Now for these, I did remove the fertilizer spikes just to keep this clean. So for each of these is the dissolved P and the particulate bound P for field number 8. And so what we see, again, as we saw in the previous, is that the dissolved P tends to stay within a fairly tight range across years for that field, because the soil test P is not changing rapidly. But the particulate bound P can have a huge range. It also generally is considerably higher than the dissolved P. Now these are concentrations again. And so we see these huge spreads, but generally for concentration, the runoff particulate P tends to be considerably higher than the dissolved P. Now let's move into load. This is pound per acre of what we see coming off the fields. But now I looked at the ratio of runoff particulate P versus runoff dissolved P. So we divided runoff particulate P by runoff dissolved P for each runoff event that we were looking at. And we can see a big range in what we're seeing. So now these bars here, sometimes you can hardly see them. That's the average for that sampler, for that spread. And so we see that on average, runoff particulate P is 1.6 to 28 times higher than the runoff dissolved P. And the average of all of that, it's about 10 times higher. So on average, we see, and this is across all the different soil levels and across all the different management practices, we see in general that the runoff particulate P is about 10 times higher than the runoff dissolved P. Okay, so how was all this raw data used? So we used all this raw data to develop the On-Field Ohio tool. And so we were quantifying edge of field erosion and P runoff based on field properties and farmer practices. So, and as I say, so we calibrated the On-Field Ohio tool using actual measured field data. So I will go through this very briefly. I'm sure a lot of you have seen this, but I just wanted to show it one more time. So this is our Malick 3 soil test P again, and how it's related to, this is on concentration, our runoff dissolved P. We actually took our soil samples, the diamonds are at the 0 to 2 inch depth, And the circles are at the 0 to 8 inch depth because we wanted to see, does it matter? Do we need to do it a specific way? And you can see that both of them had an excellent relationship to the soil test P, and the equations for these lines were not terribly different. So we went forward using the 0 to 8 inch because that's probably more representative of what typically is done. So now for these, we're going to look at how we came out with this is the on-field Ohio estimated versus the actual measured. So on-field Ohio estimated versus edge of field measured. And what we're looking for in these is we want a slope near 1, and we want a very highly significant R squared. So this particular graph is for the measured versus estimated surface runoff dissolved P. Now we're in load, pound per acre. This is for the surface particulate bound P. This one is for the surface runoff total P. Now we'll move into the tile. So we're back to concentration here, but this is the tile on-field Ohio estimated versus measured, and the blue is the dissolved P, and the black dots are the runoff total P out the tile. And here it is for load, for runoff tile. So this is everything all together, all the dissolved, all the particulate bound for both surface and tile, all added up. And we see we have a highly significant relationship. And then this I haven't shown a lot, but because this is coming up more and more, probably because I'm bringing it up, I would also like to show that for our study fields, if we look at the Russell 2 erosion that we measured on our fields, that's highly correlated with both the runoff suspended sediment, which was the amount of mud that we actually found in our runoff bottles, sample bottles, and the runoff particulate P concentrations. So resulting of all of that is we developed the on-field Ohio tool, which, you know, probably some of you have seen, and, you know, maybe another day I'll be invited and I'll take you on a tour through the on-field Ohio tool. But I want to, in the interest of time, I want to move on. Okay, so now we know all this stuff. We know what's coming off the field, and we can predict it using the on-field Ohio tool. So what does that mean as we look across Ohio? So, and Chris did a great job of discussing this, that the US-Canada binational agreement, we're looking for a 40% reduction in phosphorus loads into the Western Lake Erie Basin. But from my standpoint, it's like, well, what about all of Ohio? What can we reduce from the other watersheds? So using simulations of the on-field Ohio tool, we can compare what if scenarios. So to develop these scenarios, we took actually 2 million random points around Ohio, and then we filtered out anything that was not row crop agriculture. So we took out the cities, we took out open water, we took out roads, we took out forest. And so this represents what was left. We have more than 6,000 data points of row crop agriculture in Ohio. So at each of these points, using the on-field Ohio equations, we can measure the erosion using the Russell 2 on each of these points. And then at each point, we of course have to load in all of the soil survey data in order to measure Russell 2, the erosion. And then to do these, we had to assign a crop management scenario and a soil test P level. So the soil test P levels came from a random selection from a survey we did of the 3 big soil test slabs. So for each, from this survey data, we got the soil test, we used the 2015, I believe, soil test data, and we got the data at a zip code level. So for each random point location, we would randomly select a soil test P level from this survey from that same zip code where the point location resides. A little confusing. So this is what the assigned Malik 3 soil test P levels look like across Ohio. And we found that it mirrors pretty closely what the soil survey distribution looked like, as it should, since that's where it came from. So this shows that, you know, for a lot of soils, they're within the agronomic range. But the whole range that's actually represented here goes from 3 to more than 1,000 part per million soil test P. So again, because we want to see what the range, what's possible, what could happen out there, we wanted to select crop management scenarios that represented a broad range of soil disturbance. So we use the soil tillage intensity rating, which can range from 0 to 100. And in consultation with OSU Extension and Ohio Department of Ag and USDA, this is what we came up with. So these are all bean corn 2-year rotations. So we have no-till, no-till, so all no-till. And then the second, we have no-till beans, but we did a fall vertical tillage and then no-till corn. And then this is probably common in Ohio, more of a rotational tillage. We did no-till beans, but then a fall chisel, and then a spring cultivate before corn. And then this one we threw in, and this was requested just with lots and lots of crazy tillage. I don't think anybody is doing this in real life. But again, when you're doing research, it's good to see the full range. So this is what erosion, now we're going to go across the state. This is what erosion would look like across the state. So at each point location, we ran each of the crop management scenarios. So this is 24,000 data points. So this is the no-till, this is the vertical till, this is the rotational till, and this is the crazy till. So we can see that if the dots are green, we're less than 1/4 of a ton per acre per year. But then when they start to turn black, we're at greater than 4 tons and sometimes way greater than 4 ton per acre per year. And so the point of this is to show that, you know, in the Western Lake Erie Basin, it's hard to even get your erosion kicked up because of the low slope. But when you get into the more rolling areas of Ohio, the erosion can go up quickly and substantially. So again, now we're back to look at the surface runoff load for dissolved reactive P. Again, this is really sensitive to your soil test P levels, not really very sensitive to erosion or slope steepness. So this is what it looks like across Ohio based on that distribution that I showed you earlier. And this would also be similar for tile because, again, a dissolved reactive P coming out the tile is also related strongly to the soil test P level. And again, notice we're going from less than 0.16 pound per acre per year to about 1/3 of a pound. Well, it can be greater than 1/3 of a pound per acre per year of phosphorus loss. But then we get to particulate P, things change dramatically. So again, with the no-till, rotational till, and the crazy till, now we can see, again, we have a huge effect of topography. And it's, if you're in the flat area and you don't have a lot of erosion, your runoff particulate P can still remain fairly low. But as soon as you get into the rolling areas where erosion starts to really pick up, then your runoff particulate P can increase dramatically, because now we're at, 1/2 pound per acre loss to greater than 4.5 pound per acre loss. So I want to belabor that a little bit. So the way I set up the legends, and I kind of wish I hadn't done it this way, but I thought I was being clever. I set it up based on percentile breaks. So we did 0 to 20, 20 to 40, greater than 80 percentiles. So if you're at the 60 percentile, that means 60% of your values are lower than 0.22. So but the important thing is the comparison between what we saw coming off for the dissolved P or the runoff particulate bound P. So let's go back to our ratios. So if I divide the runoff particulate P by the dissolved P, and again, I should point out, because the B is to clue me, to remind me that this is baseline. So I really did take out the fertilizer spikes. There's not that many of them, but I just want to look at what's coming off the field all day, every time there's a runoff event, independent of what a fertilizer application could potentially do. So we see that even in the 20th percentile, we can be, up to 3 times higher for the runoff particulate P than the dissolved P. And then as this increases, so you can be up to more than 15.5 times higher in runoff particulate P than in dissolved P. And I think I hope I made the point earlier that these increases are because as erosion is increasing. So in the simulations, the range from 3.2 to 15.5, greater than 15.5 times higher than dissolved P for runoff particulate P. And that mirrors what we saw in the measured data, where our runoff particulate P was 1.6 to 28 times higher than the dissolved P. And on average, it was close to 10. And here we see our median is, we're 10 times higher in particulate P than dissolved P. So I hope I'm making the point that, we really need to be watching our erosion. So and I threw this in also to show, because I know people are going to ask. So this is everything. This is surface plus tile runoff total P. So before this was in the middle, was up to 2.3 pound per acre. Now we're at 2.84 pound per acre. And this was at 4.5 pound per acre. Now we're at 5.13. So it, obviously the dissolve contributes and what comes out the tile contributes, but it's the surface particulate bound P runoff that really seems to dominate the runoff P risk. So then the next question is, oh my God, well, is there any hope? Is this 40% reduction goal achievable? So again, we can go back to our what if scenarios. So as they say, well, I've showed you 4 crop management scenarios. So if we say, well, let's say that we move all the way from our rotational tillage or vertical tillage, and we move all the way to no-till. What would be the reduction in runoff P? Now, I want to acknowledge here that I'm not intending to push that. I'm not suggesting that every farmer should do that at all. I just wanted the examples to illustrate the importance of reducing soil disturbance and erosion, and also to make the point that field cover is important because that's weighs heavily on how much erosion you have. So I just wanted examples to show that as you reduce soil disturbance, what kind of reductions in P runoff you can expect. And we've seen it in our fields. We've seen these actually happen. So I can't even see okay, so this is runoff particulate bound P reductions. So if we move from the rotational tillage all the way to no-till, and this one is if we stop doing even the vertical tillage and move all the way to no-till, these are the percent reductions in runoff particulate bound P that could be expected. And so for this one, we see, lots of blue, yellow, and pink dots predominantly. So that means we're reducing particulate bound P by greater than 50% and up to 86% reductions in runoff particulate bound P. Now, because the vertical tillage wasn't as disturbing as the rotational tillage, the chisel, here we see that our reductions are primarily in the greater than 50% to 80% reductions. but that's really good news. That's what everybody's looking for. And remember that in all of these examples, we did not change soil test P at all. The only thing we changed here was crop management. So, so these are the reductions that we would see in erosion by, again, no more chisel. We're going to go all the way to no-till. No more vertical tillage. We're going to go all the way to no-till. And so here again, we see the similar, greater than 78 to 91% reductions in erosion. And for this one, we're seeing from, 78 to 83% reductions in erosion. So that mirrors really strongly what we're seeing in the runoff particulate P. But now let's look at the broad, zoom out a little bit. So these are percent reductions in surface plus tile runoff total P. So we just added back in the surface and tile dissolved P back into this, and the tile particulate P. So this is everything. So the reductions don't look quite as dramatic because we just put all the dissolved P back in, and that won't be affected by changes in erosion. But we still see hefty reductions potentially possible, 5 to 78% reductions would still get you where you need to be. And even for this one, there's some pink dots, but it could be 5 to 66% reductions. So yes, there is hope that by reducing erosion, we can reduce particulate P runoff. So that was a lot. So the data is saying that the runoff risk is predominated by erosion driving runoff particulate bound P. And that tends to be considerably greater than the other risk of erosion, which is a high soil test levels, which drive the risk for dissolved reactive P, and probably greater than, and that's probably a little bit greater even than the short-term risk of a fertilizer or manure application. So, and the other thing that the data shows, in the interest of time, of course, I didn't bring everything, but banding and injecting of fertilizer or manure is always okay, and it's just wonderful. And it's just brilliant at getting rid of those fertilizer or manure spike events. But if incorporating, and that's a dirty word that we're always discussing, but for example, if you're going to surface apply fertilizer or manure and then run over it with an incorporation tool like the vertical tillage or the chisel, be aware that if you increase your erosion risk, you may be better off to just surface apply the fertilizer or manure and not run the soil disturbance tool. So, and the other thing, and I think that, Chris made the point with the discussion of the legacy P, you can't change your soil test P fast. So if you have a high soil test P, well, that's a tough situation to be in for water quality, but you can change your management. So if you reduce your erosion and you keep that soil and therefore that P on your field, you could have a big reduction in your runoff risk. And yes, finally, there is hope. But the erosion reduction is probably your fastest and bestest fix for P runoff problems in the short run. And that's what I brought today.
Okay, thank you, Libby. We appreciate all the slides and the good data that you brought to us here. At this time, we'll go ahead and take questions. If anybody has some, type them in the Q&A box. I know we have a few other questions here that have been sent to us privately. So I think one question I have on this may be for both of you. Can you, we talk about total phosphorus and then dissolved reactive phosphorus. I guess I've seen some stuff coming out on the TMDLs, and there's some want to have both of those addressed in this future TMDL. Are we able to correlate if we have a certain amount of total phosphorus? Do we know what level of dissolved reactive phosphorus will be in that, or is there research being done on that?
I'm happy to
I
take the
think,
first cut. Go ahead, Libby,
oh,
please.
no, you go ahead, Chris, and then I'll correct you.
I love it. I need that. That's perfect. For sake of time, I didn't go into the difference. Sometimes you see DRP, sometimes you see TP, sometimes you see particulate P. The other one we see is what's bioavailable phosphorus. And so what that is it's the dissolved, because 100% of the dissolved phosphorus is available to grow a bloom. But that particulate phosphorus, only a portion is available, because those organisms have to be able to strip it off the soil particle or strip it off whatever it's attached to. Right now, what I'm seeing, and most of it's coming out of Heidelberg, but I'm happy to know if Libby knows other things too. Usually we say, I've seen numbers of 8% all the way up to 30% of the particulate phosphorus is available to the organisms. So most of us don't talk about DRP being available, we talk about bioavailable. So that's all the DRP plus a percentage of the particulate P. So that's the problem when you talk about total P. It depends, because you need to know how much of that total P is particulate, and then you need to know how much of that particulate is readily available to grow organisms. So the answer is we don't know. We can't make that statement. And the other answer is, as it always is in science, it depends.
Okay, well, I'll pick it up from there. So this question comes up so often, and I actually did a study and I looked at the bioavailable P of our study soils, of the soils in our fields. And I do realize that what Heidelberg sees at their gauge stations does range from 8 to 30% bioavailable. And I've said this 100 million times, but the time it gets there, it's already very well rinsed through the drainage system, the stream systems, and the river systems. So the question that I had is, well, what if we measure, there's standard methods for measuring bioavailable P and sediment. So I applied those methods to our field soils. And for those, it came out, probably, I don't have it right in front of me, but 30 to 85% bioavailable. And that's saying that would become available if that soil got eroded into the water and started to release phosphorus into the surrounding water. And also remember that is happening every time soil gets eroded into the drainage system. A good portion of more of it is probably dissolving in the drain system than would be in a short-term rain at our samplers. So by the time it gets to where Heidelberg's measuring it, they're measuring a good bit of that as dissolved reactive. And that means there's less still bound to the soil. So, if we just took a conservative value and said that it's 50% bioavailable, that still would mean that on average, the bioavailable P coming from the particulate P would be 5 times higher than the dissolved P coming off at the edge of the field. And that is an important distinction. And, I do have, I was invited, I give a presentation about the soil test P. The other thing to be aware of is the soil test P, the Malic 3P, measures about 10% of soil total P. So when those soil particles get eroded into the drainage ditch and start flowing, it isn't just the Malic 3 that's vulnerable to dissolution. It's all the P in the soil is vulnerable to dissolution. And so that might be a talk for another day.
And the only other thing I'll add here is, and this is early research, so we don't have any, a level of data where we're ready to publish on it, but Jim Hood out of OSU is also showing that, again, as I mentioned, most of the phosphorus comes down during these heavy storm events. We have always historically thought of these rivers as just pipes. They take what comes off the land and shove it into the river. He's actually showing too, not only are these particulate phosphorus being released as dissolved, but there is some absorption that's happening. So the sediment particles are actually grabbing dissolved phosphorus back onto a sediment particle. So are the rivers acting as sources of phosphorus, all that the phosphorus on the bound sediment coming in, or as they acting as sink? And I would it's not just going one way. It's not just being released from particulate, it's also being absorbed. So we need to find out are rivers sources and sinks, and are they sources and sinks at particular time of year or size of storm events? There's still a lot of work to be done there too.
And I would agree with that completely, because that is a well-known phenomenon, but it's a hard one to, to track or to measure. But I think I would also go back to something that Chris showed in his talk, where he talks about 79% of the P load comes in 20% of the flows. And I think that goes back to one of the earlier plots that I showed with all those pink dots that were, really high, because that's what we find with our farm fields, is that it's those gully washer rainstorms that really drive most of what the farmer is losing across the year. But again, that's driven by the particulate P that's coming off the at the edge of the field. And I would also put in the caveat: the farmers are never going to be credited by the source and sink discussion in the river system and in the streams and the tributaries. They're always going to be judged, for lack of a better word, by what's happening at the edge of their field. So I think Chris's point is well taken, but I think that if we focus on what's at the edge of the field, hopefully the rest of it will take care of itself. Hopefully. Yeah.
Good, thank you for that great discussion on that. We have one question here in the Q&A talking about legacy soil test phosphorus. So have there been any studies done on harvesting more than one crop per year to reduce that? I'll go along with that on the legacy side. And when we see these legacy fields, sometimes we don't need to add phosphorus, but we may not get the crop yield we expect out of it. So how do we manage that when we're looking for specific yields? And when we have higher yields, we can pull more phosphorus from the soil. But for the first part of the question is, has there been any studies on harvesting more than one crop per year?
Yes, there's been many of them. And a lot of them, they're they'll dice it finely to, how much will be cropped down if you plant corn for grain or corn for silage. How much if you crop hay. I mean, there's been a ton of work on that, and they all agree that, yeah, it'll go down, but it's so slow. It's almost, and I will take exception with one of your statements that even if you have a high legacy P, you made a statement, you may not be getting the yields, but that will never be because of phosphorus. The one thing I will always say to farmers is trust your soil test. If your soil test says you have enough P to grow your crop, you do. I mean, that may be coming from nitrogen. If you're having a reduced yield, it may be coming from, weather. So I think you can trust your soil test, and we strongly recommend cropping down, but it is painfully slow. And I know Laura Lindsay has been looking at doing some double crop stuff. And part of that is for cropping down phosphorus, but then part of it is just for farmers to make more money. But yes, the short answer is yes.
And just to add to that, right, it's easy to, we should be planting asparagus. Everything I read is asparagus sucks down a ton of phosphorus, but if you don't have a market for it, and if it doesn't fit in that farmer's lifestyle or what they're able to do, it's not easy to make some of those transitions. I think it is a creative solution and it'll work well in some situations, but it's definitely not the silver bullet for us. And so I agree, Libby's spot on with all of this. I would say that if you have a legacy field, two things in this legacy field, you saw from those 3 counties that I showed you, that drawdown is pretty slow. What I hope we're suggesting, and a lot of our certified crop advisors are suggesting, is we have the tri-state bands, the ranges, but I would suggest we don't need to be shooting to apply at the top of that range. We should be shooting to be in the middle, because it's not like if you can't get out there for 2 years, you have no crop, right? It draws down slowly. So I would recommend, I'm not a certified crop advisor, but what the data is showing me is that we don't apply at the top end of that range is one of the things that I would say.
Agree with that. And I hope that, I hope if farmers would take that as good, that, save yourself a ton of money trust your soil test and trust that it's going to remain steady for years. Now in our fields and, our really high level fields that we show, we had a couple of them. And, we probably didn't need to go out and soil test every year, but we did because we said we would, and it didn't change at all. And that field had not received any fertilizer or manure for like more than 15 years. So that truly was a legacy field. And then I was out there recently again for a different project and we collected more, and it's still 350, 400. It's not changed at all. So trust your soil test and have
The
faith.
last thing I'll mention here too is I'm trying, and I know Libby's doing it, a lot of our extension folks are, and then the water quality is, I wish we would stop talking about farming to yield, but farming to profit. Because if you don't have to apply fertilizer because you have a legacy field and you're not getting the bushels of corn you used to get before, your profit is still higher probably because you're not paying for the fertilizer. So if you don't apply fertilizer because you've got legacy high phosphorus fields, but your yield is what you're not used to, think about your profit, not about your yield.
I concur.
Yeah, and I think we've heard a lot more discussions on that this fall as we've seen fertilizer prices start to go pretty high for next season. So we may, through a different avenue, have those discussions and be better in the long run for our soil and our waterways. Chris, we have a question here. How long do you foresee the HABRI program continuing to fund research? And then what have you learned about the movement of HABs through the HABRI research?
Yeah, great. So it's the way that gets funded is through what's called the Ohio Department of Higher Education. It's what's called Third Frontier. So it's not necessarily a legislative thing. We don't need the legislature to prove it. So as long as the governor's on board, that can continue in time. What I would say is I'm happy is usually we were getting 2 million a year. In the current biennial budget, we got bumped to 2.5. And I think the reason behind that, many reasons, but the key reason is that the governor was seeing that the research coming out of here is not only informing HABs, but it's informing H2 Ohio. So where the wetlands go and the practices that they're paying farmers to do. So I'm optimistic, knock on wood, that it continues for quite some time. But it is not a biennial budget allocation. It's a bond issue. It's another mechanism. So I'm hoping for a while. And then to the second part of that question, I kind of got lost a little. So what about HABs and the direction we're going? Can you rephrase?
I think what have we learned about like the movement of HABs through this type of research?
Yes, as far as movement in the system, basically we found, usually we used to say if there's a green scum on top, all the toxins are at the top. Pretty much all of our research is saying is those toxins are spread throughout the water column. There's enough internal movements and currents in there. We hoped, excuse me, that we could tell our water treatment plant operators that only pump water from your pipes when there's a surface scum, because then the toxins aren't at the bottom. But we found out that those toxins are throughout the water column. As far as movement of those HABs, we have a good ability to predict how big a bloom might be in a year, its maximum size. But as far as where it's going to be in the lake at any given point in time, that is completely driven by wind and wave action. Sorry. So there is a forecast or a bulletin that goes out bi-weekly, and I can get you the link to that. It's NOAA's HAB forecast for Lake Erie. And basically they'll tell you where the bloom is now from a satellite. And then based on weather predictions, they'll tell you where it's likely going to be in 72 hours.
Okay, we have another question in the Q&A talking about just soil test variability throughout a field when we have varying soil types. So we may have some heavier ground or some sand in the same type of field. So what kind of research or what are we looking at as cost-effective ways to address that variation? Is there anything being done beyond just a VRT, so to speak?
Well, I think that the variability in soil test P is always somewhat of an issue. And when we did our soil testing, I think we tested, we took a soil sample every 3 acres. And if we had a smaller field, we took at least 3 soil tests. We tried to get the points, scattered around. And so we tried to get at least 1 point in each of the soil series within the field. And we didn't find that made much difference. I mean, the first couple of years we worked at that really hard. We didn't find a big difference. Now, what I found interesting was that a lot of our farmers were already doing grid or some other VRT sampling. And then they would share that data with us. And if we looked at the average of what they came up with and the average of what we came up with, they always matched. So I think that I don't think you could go too far wrong, but we did do every 3 acres, which I think is pretty heavy. But and as also, since it doesn't change very rapidly, you can do different places, different times. And of course, that's the caveat. If you have a low spot that's wet and always has a problem, that always has to be handled separately. But that's how we did it, and it worked out without any problem.
And so with that, would you say that the variable rate application of fertilizers is helpful going across a field like that? Or if you're saying there isn't as big a change, that's not going to make as big a difference?
What I found is with, and again, there's people who know more about this than me because I'm not an agronomist, but with the variable rate folks that we saw, we did not see huge differences in, again, this is phosphorus. There might have been for nitrogen, but we didn't see a huge range in their different zones for phosphorus. And so definitely, if you can apply variable rate, that's a great thing because eventually you'll get your field evened out. Or if you've got a dead spot, you can just skip it completely. So I'm a fan of variable rate, but I wouldn't, don't be a slave to it if it's something that you're not set up to do. Just trust your general soil testing is okay too.
And I've got to drop off, but also it'd be good to look at yield maps too, right? To lay over the soil test with the yield maps. That's enlightening in that practice. But I'm sorry, I know it's not 11:30 yet, but I got another call coming in, so I got to go, folks. Thank you for the opportunity. Libby, great to see you. Great talk.
Always a pleasure.
Yeah, thanks, Chris. Well, Libby, we have one more question here for you, and then we can wrap up unless some more come in with the Q&A box. When we talk about no-till fields and soil losses versus subsurface placement of nutrients, is there a big difference between, like, if you're looking at a no-till situation versus doing a strip till situation? Do you see huge differences in that case?
Well, again, the scenarios I chose, I kind of now wish I'd done a strip till because I do get that question. But soil disturbance is a gradient. And so, if strip till is, well, it's probably going to be less than a chisel. And so you will see those reductions. Strip till is definitely better than probably a chisel. The on-field Ohio tool you could run both of those scenarios and compare them very specifically at the field scale. And then that helps. That's what we hope that farmers will do, is run different scenarios to try, based on what equipment they own and their field situation, you could look at different scenarios and then pick what fits you best. And
Great.
then,
What?
I'm sorry, go ahead.
Nope.
And then back to we didn't see any problem with banding or injecting fertilizer in any of the scenarios that we ran. That's always okay.
Good. Okay, well, with that, I think that wraps up our question and answer period. I'll turn it back over to Rachel to finish up.
Yeah, thanks so much, Jordan. Great discussion there with Libby and Chris. I'm putting up right now the CCA code if anyone needs those. Can you see it all right, Jordan?
Yeah, we can see it. Thanks.
Okay, great. So you'll be getting half an hour of nutrient management credit and half an hour of soil and water management credit. And while I leave that up, I'm going to drop in the chat one more time the link to our survey. So if you would please take that, it'll give us some great information about what you learned from this presentation or group of presentations and how we can better plan for future programs. So I'll leave this up for a few minutes. And if you have any requests for documents or anything to be included in the follow-up email, go ahead and put those in the chat. We already had one request for some of Libby's information to come in. So we'll get that out with the follow-up email and the recording link. So thanks so much again for joining us, and we hope to see you at our next Water Quality Wednesday.
Thank you.